Assalamu alaikum everyone. Welcome to the course of Real-Time Embedded System. Today we are going to talk about general purpose processor. This is going to be our lecture number 9 and this is chapter number 3. Previously we discussed custom single purpose processor design. I hope the things that we discussed in that chapter are clear to you, and now we'll talk about general purpose processor. So let's start it. So let's start with the introduction of general purpose processor. A general-purpose processor is a programmable digital system intended to solve computation problems in a variety of applications. Same processor can solve computation problems in various applications, for example, communication system, automotive industry, industrial embedded systems. There are several benefits when an embedded system designer uses general-purpose processor to implement system functionality. Number one is, first, the unit cost of designing is very low. It's almost few dollars, and the reason for this, processor manufacturer can spread its NRE cost for processor design over large number of units, ranging from million to billions. For example, Motorola sold half a billion microcontroller 68HC05 in 1996 alone. Okay. Second is, the processor manufacturer may thus use experienced computer architects who incorporate advanced architectural features, state-of-the-art IC and VLSI layout for critical components. Now these factors improve design metrics like performance, size, and power. Number third is, the embedded system designer may incur low NRE costs since the designer need to write software and then apply compiler or assembler, both of which are mature and low cost. Likewise, time to prototype, time to market will be short since ICs can be purchased and then programmed in designer lab. So flexibility will be great. You can rewrite the program very easily. One thing more that I would want to add here is that general purpose processor have separate program memory. They have general data path. Embedded system designer simply uses them. So let's go and check out the details of general purpose processor in detail. Moving over to next slide. So in this slide we are going to talk about the basic architecture of general purpose processor. As you can see in this slide, that general purpose processor consists of three main components, and sometimes we call general purpose processor simply CPU or microprocessor. It consists of data path, control unit, and memory unit. The memory unit is tightly linked with control unit and data path. The control unit comprises of controller that is connected to PC and instruction register, which is then connected to memory for getting the instruction from memory, and PC program counter is used to fetch next instruction and it increments itself when instruction register fetches instruction. Whereas data path consists of general purpose ALU registers, and the registers are connected to memory. Control and data path are connected through status and control signal as well as through input-output signals. Now, their operations are performed in data path as you can see in this slide. Now, you can see in this slide that multiple operations are performed in data path. For example, starting with the load. Load function read memory location into register in which contents are 10. So you can see the load will read the contents from the memory location in which the contents are 10, and it will load these contents to register. So you can see. Now ALU operation, from register the contents goes to ALU. After incrementing it come back to register. Now the content is 11. So the operation that is performed by ALU is to increment 10 so that you can see increment takes place in ALU, and now the value of 11 comes to register, and then in final stage we can write register to memory location. So now write the content of register to memory location, so 11 will be stored in the memory location. So this is how we can perform operations in Datapath. So in this slide we are going to talk about the control unit. The control unit consists of circuitry for retrieving program instructions. The program counter holds the address in memory of next program instruction to fetch. Instruction register to hold the fetch instruction. Now controller consists of state registers and control logic as we saw in chapter number 2. Now for example, if we have a 16-bit program counter, it means that we have 2 raised to power 16 memory location. We typically call it 64K memory. So the processor address size is going to be 64K. Now, instruction cycle is typically broken into several sub-operations, each one clock cycle. For example, we have fetch. In fetch, get next instruction in instruction register. In second, decode, determine what the instruction mean. Third, fetch operand, move data from memory to data path registers. Number 4, execute, move data through ALU. Number 5, that's the last number, store result, meaning write data from register to memory. So you need to make sure that each instruction is broken into several sub-operations and each one of them has single clock cycle. Now we will look into these sub-operations one by one. So let's move on to next slide. So in this, our first sub-operation of control unit is to fetch. As I have already told you, get instruction into instruction register. Program counter always point to next instruction. Instruction register hold the fetch instruction. So you can see we have 3 instructions at address 100, 101 and 102. And our program counter currently points at 100 memory location, and it holds the instruction of load R0, comma, memory of 500. So this instruction will be loaded to control unit in instruction register. Now once this instruction is loaded into the instruction register, we move on to next point, which is going to. So our next point is decoding. So decoding takes place in controller. Now decoding will determine what the instruction means. And our next step is fetch operands. So in fetch operands, we will move data from memory to data path register. So now we are going to move the contents of memory location 500 to register R0. So as you can see here, the contents are moving from memory location 500 to register R0. So now we have fetched the operands. Now next operation is to execute, move data through the ALU. This particular instruction does not require any arithmetic operation as we are doing only loading instruction. So we are just going to move the contents of memory location 500 to register R0, which we have done already. So we do not need to perform anything during execution sub operation. Okay. So moving on to final stage, that is of store. So as I have already told you, storing means writing data from register to memory. However, this particular instruction does not do anything during this operation because this is load instruction. We are not storing anything. So that's all. This is the single instruction of load R0, M500. Now just have a look at other instructions. There is 101. Now There will be clock, so program counter is at 100, and in that program counter we fetch the instruction from the memory into instruction register. In next clock cycle we decode it, and in next clock cycle we fetch the operands, and in next cycle we execute it. However, there is no operation performed because execution is not required here. And finally, in last clock cycle we store results. So there are 5 clock cycles that are required to perform a single instruction. Okay. Now program counter automatically increments itself onto the next instruction. So in first clock cycle, the instruction 101 will be fetched and it will go to instruction register, as you can see here. In the next clock cycle, it will be decoded, what action we need to perform. In the next clock cycle, the operands will be fetched. So the operand that will be fetched are increment R1, R0. So in next clock cycle, because we're incrementing something, so what do we need to do? We need to increment R0 with 1, and we will place the contents in register R1. So you can see that R0 previously holds 10. The values go to ALU, it increments and store backs in register R1. And finally, we're not going to perform any store operation because the instruction is of increment. Now, once this subs instruction finishes off, program counter increments 102. Now in first clock cycle fetch, the instruction of store is fetch. So what we need to do in this instruction, we need to store the contents of R1, that you can see is 11, in memory location 501. So in next clock cycle we will decode this instruction. In next, operands will be fetched. However, we are not fetching any operands here. In next clock cycle execution, no execution is taking place. Finally, we are storing the result in 501 memory location. So this is how instruction cycle works, and it always works on the rising edge of the clock. So when designing a general purpose processor, we need to take care of some architectural consideration. So n-bit processor typically means n-bit ALU, registers, buses, memory data, and interface. So the size of all these is going to be n-bit. Embedded system typically have 8-bit, 16-bit, and 32-bit processors, whereas desktop servers have 32-bit or even 64-bit. And as I've already told you, PC determines address space, like the size of the address space. So these are the architectural considerations that you need to take care when designing a general purpose processor. So moving on to our next slide. So the concept of pipelining is typically used to increase the instruction throughput. Pipelining is a common way to increase the instruction throughput of a microprocessor. We first make a simple analogy of two people, as you can see in this diagram, approaching the core of washing and drying 8 dishes. So 1, 2, 3, 4, 5, 6, 7, 8 are 8 dishes that a person is washing, and then second person is drying those 8 dishes. Assuming 1 minute per dish per person, this approach requires 16 minutes. Obviously, we will need 8 minutes to wash, and then we will need 8 minutes to dry them. So overall, in non-pipelined approach, dish cleaning would require 16 minutes. This approach is clearly insufficient since at any time only one person is working while the other person is idle or free or doing nothing. Obviously, a better approach, as you can see in front of this figure, is pipeline dish cleaning. So a better approach is for the second person to begin drying the first dish immediately after it has been washed. So this approach requires only 9 minutes. 1 minute for the first dish to be washed and then 8 more minutes until the last dish is finally dry. So once the first dish is washed, the second person will dry it. So once the last dish, that is dish number 8, is washed, the second person will dry it. So total we will require only 9 minutes. So we are kind of saving 7 minutes. Okay. So this is how we can increase the throughput of the instructions. Okay. So now think of each dish is like an instruction. Think each dish is like an instruction. And the two tasks of washing and drying are like 5 stages. So as we have seen that each instruction is subdivided into 5 sub instructions: fetch, decode, fetch operand, execute, and store. So now think of two tasks. Washing and drying are like 5 stages as listed previously. By using a separate unit for each stage, we can pipeline instruction execution. After instruction fetch unit fetches the, as you can see in below diagram of pipeline. After the instruction fetch unit fetches the first instruction, the decode unit decode it, while the instruction fetch unit simultaneously fetches the next instruction. So let me highlight. So once this instruction was fetched, now in second it was decoded. So when it was decoding, the second instruction was being fetched. Okay. So now we require almost like 5 minutes. You can see here we required 5 minutes for first instruction to be executed. After that we will require only 7 minutes to execute rest of the instructions. So these 8 instructions will be executed in 12-minute time. As you know that each instruction required 5 sub instructions. Okay. So once the first instruction is fetched, in second cycle this first instruction will be decoded while the first will be fetched. So you can see that when the first instruction is like we are fetching the operand of first instruction, the second instruction is getting decoded. Okay. And when we are executing the first instruction, the second instruction operands are fetched. And when we are storing the first instruction, the second instruction is being getting executed. So we required like 5 minutes for first instruction, and then we required 7 minutes for rest of the instructions. So these are 12 minutes. Okay. You can count the lines at the bottom: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is how pipelining is done. Okay. Now there is some issues like branches pose a problem for pipelining. When we have a branch statement, we do have some issues because we have to transfer our program counter from one place to another place. Since we do not know the next instruction until the current instruction has reached the execution stage, one solution for the branch problem is to stall the pipeline. Once we have branch instruction, we usually stop the pipelining. When a branch is in the pipeline, waiting for execute stage before fetching the next stage. So we want the execution stage to happen before we fetch the next instruction. So that was it about the pipelining in order to increase the throughput. Now let's move on to next slide. So in this slide we are going to discuss about the two widely used memory architectures that are used in general purpose processors. So first of all, let's talk about memory. So memory serves processors medium and long-term storage requirement, whereas registers serve as short-term storage requirement. We can classify stored information would be program or data. Program is a sequence of instructions that cause processor to carry desired functionality, whereas data information represent the values of input and output that are being transferred to program or from program. So, as you can see in the diagram, we have a von Neumann architecture. Von Neumann architecture has combined program and data memory. Von Neumann architecture is also known as Princeton architecture, as you can see in your book. Princeton and von Neumann architecture both are same. Now it has fewer memory wires. Its architecture is very simple. On the other hand, the Howard architecture has separate program memory and data memory. You can access simultaneous program and data in Harvard architecture. Most DSP use this architecture. Even 8051, which is very popular microprocessor, have this Howard architecture. As we are talking about the memories, it's worth mentioning here that we have two types of memories. Number one, we have ROM, that is random read-only memory, and we have RAM, that is random access memory. Embedded system uses ROM as program memory. So embedded system most of the time uses ROM as a program memory. Other data of course requires RAM. Memory can be on chip or off chip. Processor access on chip memory faster in one cycle compared to off chip memory. However, we are limited about the capacity of memory on chip, so we need to go on off chip. However, whenever we have a memory on chip, processor will access it faster compared to off chip memory. So that was about the two memory architecture. Let's move on to next slide. In addition to ROM and RAM, we have another type of memory which is known as cache memory. Now memory access may be slow. To reduce the time needed to access read or write memory, a local copy of portion of memory may be kept in a small but specially fast memory called cache. As you can see in this figure, that processor is directly connected to cache and cache is connected to memory. So what we can do, memory which is very slower, cheaper technology, and it is usually on off chip, whereas cache is very fast and is on chip, means that it is on processor. What we can do, we can move a local copy of portion of memory into cache. So we have two types of cache. Number one is D-cache, which is known as data cache, and then we have I-cache, which is program cache. Now, if the copy is found, we will have hit, or if the copy is not found, we will have a miss. So if copy of location of memory resides in the cache, we have a hit. If a copy of location does not reside, we have a miss. So if the copy resides, we have a hit. If the copy of location of memory does not reside, we have a miss. So that was about the cache memory. Let's move on to next slide. So when designing a general purpose processor, we need to understand the programmer view. A programmer usually writes the program instruction that carry out the desired functionality on the general purpose processor. Programmer does not need detailed understanding of the architecture. Instead, it only needs to know what instruction can be executed. There are two types of instructions that the programmer needs to understand. Number one, assembly level instruction, which are closely related to machine language. And then we have structured language instruction, which are either in C, C++, Java, and etc. Most development today done using structured languages because they are easy to write and easy to understand, and you do not require low level understanding of the instruction. But some assembly language programming may still be necessary, so the programmer must need to understand the low level language up to some extent. He or she needs to understand what is jump instruction, what is move instruction, what is load instruction, what is store instruction. So instruction like that, commonly used instruction, must need to be understood. Drivers is a portion of program that communicate with and or another device. Often have detailed timing consideration, extensive bit manipulation. Assembly language may be best for it. So whenever we are going to write a driver which communicate with some other device, the timing consideration are very critical here. So we need to use assembly language as assembly language best suitable for writing the drivers program. Okay, so let's move on to next slide. So in this slide we are going to talk about assembly language instructions. The assembly language programmer must know the processor instruction set. The instruction set describes the bit configuration allowed in the instruction register, indicating the atomic processor operation that the programmers may invoke. Each such configuration forms an assembly instruction, and a sequence of such instruction forms an assembly program stored in processor's memory. As you can see in figure that we have instructions, instruction 1, instruction 2, instruction 3, instruction 4, all the instructions combined together to make a small program. And each instruction you can see that it consists of opcode and operands, operand 1 and operand 2. So an instruction typically has two parts, an operand field and opcode field. An opcode field specifies the operation to take place during the instruction. We can classify instruction into three categories, as you can see in this slide. Number 1, data transfer between memory and register, register and register, input and output interface. We have arithmetic and logic instruction where we move data through ALU and back. And finally we have branch instruction, determine next PC value when not PC plus 1. So most of the time when we have next instruction we increment PC plus 1, but in the case of branch we do not have PC plus 1. Now branches can be further characterized as being unconditional jumps, conditional jumps or procedure calls, and return instructions. Unconditional jumps always determine the address of the next instruction, while conditional jumps do so only if some condition evaluates to true, such as particular register containing 0. A call instruction, in addition to indicating the address of next instruction, saves the address of current instruction, so that a subsequent return instruction can be jumped back to the instruction immediately following the most recent invoke call instruction. Okay, so we have two types of branches, a conditional jump and unconditional jump. Now an operand field specifies the location of actual data that take part in operation. Source operand serves as input to the operation while the destination operand stores the output. The number of operand per instruction varies among processors. So as we can see in this slide we have two operands. So it is not necessary to have two operands. We can have different number of operands, but it varies upon the processor. Even for a given processor, the number of operands per instruction may vary depending upon the instruction type. Even for a same processor, we can have various number of operands depending upon the instruction type. So that was about the instruction set. Let's move on to next. So there are four basic instruction characteristics. Either we can have fixed or we can have variable length size instruction. We have different addressing modes in instructions. We have number of operands. The number of operands, and I have told you that they can vary depending upon the processor type or even upon the instruction type. And we can have different types of operands. Okay, so that was all about the general purpose processor. In next lecture, we will hopefully talk about these addressing modes in more detail. Thank you very much.